Hello, everyone. So we just solved the problem, which was like a train car. I told you it was something I'd seen in Halliday and Resnick's, but this one I sort of changed up a little bit to make sure the sizes are a little more reasonable. It's actually a 3,800 kilogram box with a 200 kilogram cannon in it. The length of the box is 100 meters long, and the cannonball has a mass of 40 kilograms and will be fired at 200 meters per second relative to the Earth. And before I used conservation of momentum to calculate the recoil velocity of the train car and figured out how long the train or the ball will be in the air, because the instant the ball hits the other side, it's going to stick to that wall. And that's going to cause the momentum to go back, the total momentum of the system to go back to zero. It was always equal to zero because the momentum being carried by the ball to the right was the same as the momentum being carried by the big box and cannon to the left, but it'll actually make the total velocity zero. So the train car will have moved the distance x, which we calculated was 980 millimeters to the left. In this part, I'm going to actually realize that the box is in fact a closed system. It has no external forces acting on it if we're ignoring air resistance and friction and air resistance and everything, which we are. So in this case, we should be able to get the exact same answer just by realizing that the center of mass of the system can't change because there's no external forces on it. So now I'm going to start doing that problem using center of mass. So let me turn it on my document cam. And I have the coordinate system set up like I had before. I have the box, has a mass of 3,500 kilograms. The velocity of the actual cannonball with respect to Earth will be 200 meters per second. Before we actually calculated the velocity of the train car with respect to the Earth, and we found that was -2 meters per second because obviously it's 1/100th the total mass 40 kilograms is to 4,000 kilograms. So that's why we ended up getting 2.00 meters per second to the left for the train car. This one we're not going to talk about velocity at all. All we're going to do is calculate the center of mass of the system right now. And then after the whole train car moves what I call a positive distance x, then I'm going to calculate where the center of mass is, and you're going to see that setting that equal to the center of mass in terms of x, I can solve for x, and x will actually give me hopefully that same 980 millimeters. So let's get started. So first off, we have the center of mass of the system is actually equal to the mass of the ball, and it's of course at initial position of 1.00 meters. We have the mass of the cannon, which I call it big M subscript C, and that's also at 1.00 meters. I'm assuming everything's at 3 sig figs here. And then I have the mass of the train car, or the box as we called it, and we used a big subscript B there. And of course the center of it, if this is a uniform 100-meter long box, the center of it should be at 50 meters. Again, assuming 3 sig figs over everything. Now all of that will be divided by the total mass, which is MB plus MC plus M big B, which equals 4,040 kilograms. Okay, so if I go ahead and calculate all this, it's not as bad as it sounds. I have 40 kilograms times 1.00 meters plus 200 kilograms times 1.00 meters plus 3,800 kilograms times 50.0 meters, and all that will be divided by 4,040 kilograms. So I'll get that our center of mass is 40 kilogram meters plus 200 kilogram meters plus, now if this was 100, it'd be basically 380,000. So I got to take half of that. So instead of 380,000, I'm going to get 190,000. So that'll be 190,000 kilograms meters. All that divided by 4,040 kilograms. And that ultimately gives us that the center of mass is 47.089. I'm keeping extra sig figs for the usual reasons. Whenever you round things multiple times, you end up getting errors that build up. So that's roughly where the center of mass is before the cannonball is fired. Now, as we can see, after the cannonball is fired, everything's going to be shifted a distance x relative to where it was before. So we'll have to find the new center of mass in terms of this x. Of course, you see that the cannonball has now moved at 99 meters, so it's now at 100 meters minus x. Similarly, this cannon is at 1 meter minus x, and the box is at 50 meters minus x. So we can do the XCM again. So XCM after, I'll just put not a superscript, but just a note up there to remind us this is after the fact. So after the fact, we're going to have a 40 kilogram cannonball. That's going to be at a distance of 100 meters minus x. We're going to have a 200 kilogram cannon that was at 1 meter, and now it's going to be at 1 meter minus x. And then we're going to have a 3,800 kilogram box that was at 50 meters, but now it's going to be at 50 meters minus x. And of course, all that will be divided by 4,040 kilograms. The key point is, because it's a closed system, the center of mass can't really move. So if I set these two center of masses equal to each other, then I have only one unknown, that's x, and I can solve for that. So what I'm going to do is I'm going to say 47.089 meters times 40,040 kilograms. So what I already did was multiplied by this, by that. That's going to be equal to 4,000, 40 times 100 is 4,000 kilograms meters, plus 200 kilograms times 1, so it'd be 200 kilograms meters, and then plus 3,800 times 50. We did that before. That's 196,000. Oh, actually, times 50. Yeah, if it's times 100, it'd be 380,000. So yeah, this will be plus 190,000 kilograms meters. But that just takes care of this term, and this term. I still need the x terms. So that'll be minus 40 kilograms times x minus 200 kilograms times x minus 3,800 kilograms times x. So what I got to now do is subtract 40,000 or 4,200 and 190,000 from this product. And that product turns out to be 190,240 kilogram meters. And of course, I'm going to subtract from that 4,000 kilograms times meters minus 200 kilograms times meters minus 190,000 kilograms times meters. And all that will be equal to, notice this is 4,040, so this will be 4,040 kilograms times x. So when I do all that math, it turns out that I have negative 3,960 kilograms times meters. That's from adding up all this stuff, is equal to negative 4,040. This was a negative here, plus these all add up to be negative, kilograms times x. So when I divide both sides by 4,000, negative 4,040 kilograms, I get, lo and behold, x is equal to 980 times 10 to the negative third meters which is exactly what we got when we used conservation of momentum. So you can see that this problem of firing a cannon inside of a large, heavy box and then allowing the cannonball to stick in the opposite end is going to result in a net motion of 0 uh, for perpetually. It's going to, initially make a little bit of velocity for the box while it's got a lot of velocity for the actual cannonball. But then when the cannonball hits the other side and sticks, it's going to make the whole system come to a stop again. But all those forces are internal, so the center of mass can't move. And in doing so, I found out that that shifted the box by 980 millimeters to the left, which is exactly what we found when we worked it with conservation of momentum. And that about does it. So I hope that was instructive and helpful.